So, hello everybody, and I have just put my smartphone on to make the video for usually a publication on the YouTube. Now I must find my chalk, or a kind of chalk, and what I would like to show today will be a disconnection, a kind of case study on the molecule, which will be like that. Yeah, and chlorine group here. It is an example from that book, that PDF I have sent on the last lecture. So it is problem 351 from that book, so everybody can then see and find the solution in a standard form and compare this to what we will show during this lecture. And then we will have a kind here and a carboxylic function here, and once more here, and amine function. And once more, as usual, I'm drawing this line to delimit two types of chemistry, so synton chemistry and reagent chemistry. Synton chemistry and synton to reagent chemistry. And first, so it will be the target molecule, and first we can write some initial functional group interconversion, which will be like that. So an arrow and an arrow will be that one, so this will be an arrow. It is not a function, but it is simply a substituent in the language. So a substituent in the language of chemistry is any group having a single connection, so a hydrogen like. And then we can have here once more a carboxylic function, and here we will have a nitro substitution. So it will be the target molecule, let's say 1, because, okay, functional group interconversion, also the second interconversion, which will be like that. Okay, let's be consequent and write here simply an arrow function, and we will have once more at this side we have carboxylic function, so a carboxylic function, and then here we will have an amide function, but not here. It will be here, yes, an amide function. And let's say FGI3, in which we simply can have something like that. And here at that side we will have the nitro function. So we can see that this can be easily obtained. So if we go here synton to reagent chemistry, and we can find within the solution of this problem in the book, the answer for this will be, we have meet the nitro and CN before, but the primary amine can also be made from an amide by the Hofmann degradation, and there is a reference to the literature. So basically this kind of chemistry is well known and will not discuss them. These are a simple functional group interconversions, which is available and basically can be found in any chemistry handbook, even that for a third year course. And then we would like to ask the question, so here the reference, we can put that reference to the book, and the book is Warren, and the title of that book was, let's put it, Designing Organic Synthesis. Organic Synthesis PDF or a PDF version, which is available in that Teams, and is also available in the internet network. Once more, so let's get rid of that. So TM1, that will be TM2 at TM3. So 3 sub-target molecules available by simple disconnections, but conversions more. So functional group interconversion when disconnection. We are not making any disconnection. We are not cutting the chemical bonds. And once more, let's write that one. So aromatic, then we have nitro and carboxylic function, and a carboxylic function, and let's try to make these connections, and we'll see that not always an aromatic function, so not always this type of disconnection is the most reasonable one. So aromatic disconnection, let's say 1, disconnection 1 will not be very helpful, because we have basically a functional groups here. So a function outside an aromatic substituent or aromatic aromatic group, let's say, will interact with these connections more efficiently, providing the selectivity that would be needed for the reaction, that this aromatic structure, let's say. And so we should see that such disconnection as here will be reasonable, let's say, to disconnect. Once more, we will ask a question of how to disconnect this, in this or in that. So let's put that similarly to that, that will be the disconnection A and A1, A2, A1 and A2. And so basically after disconnection, let's write that without any changes, and let's use here this color pen to put these two. So we'll have here one blue, and the second blue is here. So with A, so 1A, we will have a minus sign here and a plus sign here. So we'll have basically a donor and acceptor here, donor and acceptor here. And once more, we'll now should ask a question: what kind of chemistry will code this donor synton? So let's put it here once more, synton to reagent, to ask a question about this donor synton, about the nitro group. So a nitro group will be like that. And we can see that once more this nitro group will be similar once more to the carbonyl function. So we know that O12 D2 D donor 2 synton is something that is well known in the chemistry of carbonyl function. And once more we can see here O12 that it will be a donor 2 synton instead of the donor 1, as we could simply think just taking into account this nitrogen only. So D1, no, basically it is a donor 2 synton that would be an analog of the carbonyl function. And so that's one, and here we have once more the carbonyl function here. So 1, 2, 1, 2, 3. So what kind of synton will be? A3. We should maybe indicate more clearly the carbonyl group here. So it will be here, carbonyl function 1, 2, 3. Everybody see it is acceptor 3. So acceptor 3, once more, acceptor 3, more clearly. It is acceptor A, now D1, and once more synton to reagent. So we would like to see the reagents. So reagents will be like that, hydrogen and a nitro function here. So simply nitromethane, and here we'll have something like that. So what I'm asking to have here, yeah, I can. There is no bond here, of course, no bond here. Something like that. It should be in that form. Why nobody improves my writing on the table? Everybody should check what I'm writing here. And once more, see what's going on. Everything is okay with my smartphone. And how should I? Carbonyl 1, 2. Yes, that's simply. No, of course, it should be like that. Yes, this should be like that. Once more to see. It is the blue. Yes, it is the blue here, and I've made this connection here. So these are two types of these are two types of yes, and once more these are carbonyl. Come on. A carbonyl function, and it is the O 1, 2, 3. Yes, acceptor 3. And now my question is how we can convert this synton into reagent, and it is simply just by putting here a double bond, and then the reaction will be simply the base, we are removing this hydrogen. So what we are obtaining is a carbanion, which is a nucleophile capable of the reaction on that center, and by the Michael addition we are obtaining a target molecule. So everybody can see that simply here we have the such a mesomeric punct once more. So such a mesomeric structure here. Such a mesomeric structure here between that two. So it shows that at this position this carbon is capable of a nucleophilic attack on that position, and after reaction we are obtaining the Michael product. And once more what we have here is we should once more put now an arrow here, so reagent to synton. So what we would like to basically to have something like that, so that retrosynthetic analysis arrow, I'll just put that here above that. Yes, it's getting too hot here, so a moment, I must remove my jacket to feel more comfortable. I'm still sleeping, and just redraw that here, aromatic function, and then carboxylic, and disconnections. Once more, where to have a disconnection, and let's try here. So near this two functions, and basically what we can see here, how to note that we'll need what is a natural reactivity here will be the donor synton, because it's an O12, so this one will be donor 2, and so we will need here an acceptor synton, and once more we can try two different positions, but let's say try that one, acceptor and donor, then I should disconnect that in such a way, and then I'll have here aromatic and then donor, and here I should have that one will be O12, so donor 2, an acceptor, and how to change these syntons to reagents, reagents. So that one, of course, so this D2 is no problem to have that kind of synton. And by hydrogen, no problem to have that one. We can also, because we know that in synthetic approaches to carboxylic acid we are using malonate instead very often. So we can have such compound. So that's a malonic acid, or alternatively malonate, and the chemistry of that is basically very well known, or should be very well known from our third year course. But what can be, so synton to reagent, once more synton to reagent, and once more we can see the solution for that is that we can have such reagent. So first, if we would like to have the acceptor, so acceptor that kind, if we have a simple chlorine or bromine, then it will be acceptor alkyl. But we can also have such a trick. Do we know such a reaction of that group with that one? Of course, yes. The answer is of course yes. An alkylation. So an alkylation, and we have even discussed such a chemistry. So if we have once more the A with a base, so then we'll have and carboanion, and we discussed that last week, that basically we know such chemistry with lithium diamine, with lithium with LDA, simply with LDA, and I cannot say it very quickly in English. I'm still sleeping a little bit in the morning. LDA chemistry is which makes this conversion from that kind of carboxylic acids and acidic hydrogen to carboanion, and then we